full disclosure, recording has started. All right. So let's start off with one of the problems that is on the problem set that I gave to you today, the one that has the picture of the Ferris wheel on it. And it says, as you ride the Ferris wheel, your apparent weight is different at the top than it is at the bottom. Explain. And then B says, calculate your apparent weight at the top and bottom of a Ferris wheel, given that the radius of the wheel is 7.2 meters. It completes one revolution every 28 seconds, and your mass is 55 kilograms. We'll do part B first because it's easier to explain part A with numbers from part B, so let's go with that. First, we have to introduce a new term. Apparent weight. Okay. We've talked about weight earlier in this class. Okay. What did we say that our definition of weight was? Anybody?
Force of gravity.
Force of gravity that is acting on you. Okay. So we've talked about weight being equal to the force of gravity. However, when we talk about a skydiver in free fall, or we talk about an astronaut, we often refer to them as weightless. Okay? Is that really the case based on this definition? Is there ever a case when somebody doesn't have gravity acting on them? Can't be. Okay? But there is something that we refer to them as weightless. Okay? When you're standing here on Earth, on the ground, hopefully this is like really reviewed, right? If we're not accelerating, how many forces have to be acting on you in this situation? 2, right? And I really, really hope at this point in time, you know, you got your gravitational force this way, you got your normal force this way. And when we're standing there on the ground, not accelerating, what's true about green and blue? Equal. They have to be equal, okay? What we feel like, sorry, let's do the next one, okay? Skydiver jumps out of a plane. How does this picture change? Okay, the bottom, I don't know if I'll be able to move the bottom. Oh, bottom's gone, right? And if the bottom's gone, what else is gone? That's not there anymore, right? That normal force comes from the ground. It comes from the surface that provides it, okay? So, in this case, what starts happening to that skydiver because of the lack of the normal force? They start accelerating, right? They start going downward faster, 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 okay? Now, this force kind of comes back with air resistance, blah, 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 but we won't go into that right now, okay? In this picture, as it's drawn currently, is this guy, or skydiver, whoever it is that skydiver weightless? Not according to this definition, but we refer to them as weightless, or refer to them as being in free fall. So that sensation of weightedness, okay, actually doesn't come from gravity. It actually comes from this. Whoa, not from that. From this, okay? When that normal force is there, that's when we become a parent of the force of gravity acting on us. If we lose the normal force, right? Anybody ever been skydiving before? Or? What? No, I never had.
One guy. Mr. Bigger than
you think?
I think that's up.
Mr. Brinker Hangel?
Yeah.
He's probably cured cancer. He's probably cured cancer as well.
Yeah.
So, but anyway, so yeah. Seeing how we're recording, we'll stop right there. Anyway,
He watches it.
that sensation. On his way to skydiving, he just peruses YouTube videos.
What if he was that guy that subscribed to you?
Vortex Lord.
That probably is it.
Totally does. Totally does. So anyway, but I mean, if you have a name like Binder Nagel, would you try to incorporate that into your username? Like, I mean, so. All right. So this sensation of weight, or what we feel as weight. JT should be having a field day over there. Yeah. This sensation of weight doesn't come from gravity. It actually comes from the normal force. And this is pretty much what your rides at Cedar Point or any amusement park sort of mess around with, and we'll talk about that in just a second. Okay? So, when we talk about apparent weight, which is now in the wrong space because I moved the picture, okay? What we're actually talking about is, what is the normal force? Apparent weight is just another way of saying what is the normal force in this situation. Okay? When I'm standing here on the ground and my normal force is exactly equal to my force of gravity, we say my apparent weight is just like normal, right? Or sometimes we'll refer to it as 1g because it's exactly equal to what? The force of gravity that's acting on me. When my normal force is equal to the force of gravity acting on me, we generally refer to that as 1g. You probably have heard that kind of thing before where we say that fighter pilots experience forces of like 5 Gs or whatever. What they're doing there is they're saying is that they're experiencing a normal force that is equal to 5 times the force of gravity that is acting on them at a certain situation. Okay? So that's what we're going to do here in this problem. Okay? Good so far? So when we say no apparent weight, all that's asking you for is normal force. Okay? Let's talk about this Ferris wheel. Let's talk about the bottom of the Ferris wheel first because it's a little easier than the top of the Ferris wheel. Okay? All right. Circle. There's our Ferris wheel. Okay? And we're going to work on down here at the bottom. Okay? So, if it says what's the apparent weight at the top and what's the apparent weight at the bottom, like we said, if it says apparent weight, what it's asking you for is normal force. Okay? Things that they gave us to work with in this problem. Information they gave us. They told us the mass of the rider, is that correct? Did 55 kilograms? Is that what it says?
Yeah.
And then it told us a radius, I believe, is that correct? 7 meters? 7.2. And then it told us a time, right? Do you remember the term that we used to reflect that, to represent that time? Called it the period, right? And it was 28 seconds? All right. Before we do anything else, let's go to this picture here. Okay? At the bottom of the Ferris wheel, 2 forces acting on our rider. What's the first force that we can put in? Yeah, that's going to be gravity force. Can't get rid of that. It's always there. Okay? But in terms of centripetal force, right, is that gravitational force hurting us or helping us? It's hurting us because which way is it pointing? It's pointing down, but in terms of the circle, it's pointing how? Out of the circle as opposed to into the circle. And we know that centripetal force has to be into the circle, towards the middle, right? The middle being this spot right here, obviously. Okay? Which means gravity can't be the only force at that point, right? There has to be another force. The only other force that's acting on the rider at that point is the seat that they're sitting on in the Ferris wheel. So that seat is providing them with a normal force. And in this case, it's going this way. Okay? So the way we're going to solve this problem, because the rider is moving in a circle, that means there has to be what acting on them? Centripetal force. Okay? There has to be a centripetal force. But that centripetal force now is a combination of 2 forces. Which 2 forces is it a combination of? Stumped you. Well, what about the blue force in this picture? Which way is it pointing? Up. More specifically, in terms of our circle, where is it pointing?
Middle.
Towards the middle. So it's got to come from that, right? But can we just disregard this gravitational force here? No, because it's acting along that same line. So the combination of these 2 results in centripetal force. This is just a net force equation, right? Is that if I apply it that way, are we good with that? All right. But we discussed a little bit on Wednesday. If gravitational force in this problem is pointing away from the middle of the circle, what should we do with it? Okay? Let's give it a negative sign, right? So we're still adding because it's still a net force thing, but then Let's call it that. Okay? Does everyone see where I got this from? Because the end result of all of these forces has to be centripetal force. Because what is this object doing? What is the person doing? Ultimately. What path are they taking? They're moving in a circle. So when it's all said and done, we got to be left with centripetal force. Okay? All right, let's start breaking this down a little bit. Hopefully by now, left side of this equation you should know, right? What am I going to substitute in on the left side of this equation? mv squared over r. What was I looking for in this problem? If we were looking for the apparent weight, I said that means you're looking for what? You're looking for normal force, so this is going to be my unknown. Then, at this point, right, hopefully we know the force of gravity, right? Like that. Okay? Do we have enough information to solve this problem right now? Not quite yet. Okay? We know the mass. They gave us the radius, but they didn't give us the tangential speed, the v, right? But they did give us enough information to figure that out. What did we say was one way that we can figure out the tangential speed? 2 pi r over t, right? The circumference of that circle divided by the period. So let's do that real quick. Let's figure out what the tangential speed is. And then we can plug that in and find out what the apparent weight is. Little less than 2 on the what? Fine with me. Now that we've got that, we know everything else in this equation that we need to figure out what f of n is. So solve for f of n. Totally. Alright, anybody got an answer for this yet? Not yet. Is it 42? No, it's got to be bigger than that. So. Does that work? Okay. And then sig dig wise, 2, 2, 2. So we probably round that to 560. Okay. Practical application. Anybody care to do this demo for me? Spin the bucket around.
Really? Oh god. I don't think he's
Not by me.
Don't worry, you're safe. Remember, like straight line, right? So, all right. So here, swing it. Stand that way. Okay. So Tom, what I want you to do for me. Okay.
Swing it and let it go.
Don't swing and let it go. Okay. So, as you swing it, right, I want you to notice something. I want you to notice what it feels like when you're coming through the bottom, and then what it feels like when you're coming over the top. Okay. All right. Are you ready? You can give a little warm up. Yeah, a little bit more. There we go. All right.
No, I think he's gonna.
All right. Anytime you're ready, you can slow it down. There we go. Okay. All right. So.
Claps for Tom, guys.
Good job.
Yeah, it's not really. All right. So before you sit down, okay. When it's going through the bottom of the motion, right? What does it feel like versus the top of the motion? Can you feel it pulling more through the bottom than you can through the top?
well, like by the time you're there, it's kind of like already going.
It is. Do you feel like more of a pull as you're coming through the bottom than you do as you're coming over the top?
Not really.
Not really? You should.
You're supposed to say yeah.
So, you should. So anyway, maybe this is not the right way, maybe not the right way to frame the question. But if we talk about like this situation here, okay, what's the force of gravity acting on this guy on the Ferris wheel? What was M times G? Maybe have that written down real quick. Do 55 times 9.81 real quick. 539.6. Thank you, Tom. So F of G is equal to 539.6. But the apparent weight here is 560 or 559. How hard does the seat have to push on you as you're going through the bottom of that Ferris wheel? Is it greater than gravity or less than gravity? It's greater than gravity. Okay? That gives you a sensation of this kind of like being weighted down. The Ferris wheel isn't really the best way, or the Ferris wheel isn't the best example of it because it doesn't go very fast. But if you think about it in a roller coaster, the bottom of that first hill, right? When you're going through the bottom of that first hill, what does it feel like when you're sitting there in the seat? Do you have that sensation of like getting pushed down kind of into the seat? Well, I mean, that's a little different situation.
How about that?
But hopefully you have that sensation that when you're going through the bottom, you get that like, you're getting like pushed down kind of feel, okay? Is gravity actually pulling on you harder at that point? No, it's pulling on you exactly the same. But the seat has to do something different to make you go back up, so you get that different sensation, okay? Now, let's flip it around and let's do the other side, okay? So let me grab the problem here again. All right. So now, let's do the top. So here's my Ferris wheel, or here's my circle again. Okay, oh, I can actually do that with that. Okay. All right, so if we talk about the person being here at the top, okay? Here's the center of the circle, right? So there has to be a force that points towards the center. If we start late, well, first let's do this. Sorry. Apparent weight means in this part here, what are we still looking for? We're still looking for F of n, right? Okay. The information that we have is still the same. Mass of 55, radius of 7.2, and then we just figured out that V was equal to 1.62, so we can save that step and just use the information from the last time. Okay? Now let's talk about forces. Okay? Forces acting on our guy at this point. What's the one we can't get rid of? That's still here. N is mean because I'm on a different page now. We still know that has to be what?
539.6.
This still has to be 539.6. That's not going to change. Okay? But when you go over the top of the Ferris wheel like this, is this the only force acting on you? If it was, what would start happening if you were sitting up there? You'd start falling. And that doesn't happen, right? So there has to be another force up there. The seat is still acting on you. But in this case, now, the seat is acting like this. Because when you're sitting on the Ferris wheel, right, when you're on the top of the Ferris wheel, the seat's underneath you, it's pushing upwards, right? Does that make sense how this picture relates to what we're doing at the top? Okay? If we go and apply it now to the problem, the combination of these two has to end us up with what? What path are we still taking in this case? You're still taking a circle. So at the end of the day, you still have to have this.
So are we like supposed to get the same answer, but like,
No.
or same problem, but this time you add?
Okay. I mean, you're making that jump, right? That's how it's going to start, all right? But now let's apply it to the things that we just talked about in the last section, okay? Which way is F of G now pointing? Towards the center. So are we going to make it negative in this problem? No, because F of G is helping us in this problem. Okay? But which way is f of n pointing in this problem? It's pointing away from the center. So f of c equals f of n, which should come out as negative. Oh, wait, hold on. Wait, sorry. Freeze that. Okay. Are we going to make f of g negative in this problem? No. So let's apply it this way. mv squared over r equals f of n plus m times g. That looks real similar to the last problem that we did, right? Except now, well, go and do it. Find out what f of n is going to be here. I don't want to ruin the suspense for you. So. We set this problem up exactly the same way, except now that gravity is pointing towards the middle of the circle, we don't make it negative like we did in the last problem. That was an epic fail. Epic fail demonstration, apparently.
What?
It was an epic fail demonstration. Didn't do what I wanted it to do.
I believe it's not.
500.
Should it be? Is it negative 590?
Subtract. Oh yeah.
Does everyone get that? At least somebody else get that? Okay. All right, so let's talk a little bit about this answer. Okay? First, the fact that it has a negative sign, indicating what in this frame of reference? Which way is it pointing? Into the circle or out of the circle? Out of the circle. So we're good with the negative sign. However, value-wise, how does this value compare to the force of gravity? Do we need to pull it back up? Here's the force of gravity, 539.6. Here's the normal force we just calculated, negative 519.6. It's what? Smaller. Okay? What does that do for us? Once again, the Ferris wheel isn't the best example. Think about the end of the blue streak. Have you ever been on the blue streak before? Hopefully you have. Okay. You know the end, like those last little hills right at the end of the blue streak? When you're going over the top of those hills, what does it feel like?
Is it like the millennium, like when you're going up it?
The first hill is not the best example, but maybe like the second hill when you're going kind of fast. Okay.
Like when you start going up. Guess I can't wait to
What is it?
Body-
Let's go.
your
Let's go.
body.
Let's go first. Let's go first with a feeling.
Your body keeps going up.
What? Okay. Your body wants to
Then you
keep
get
going
pulled
up,
down,
right?
you go down.
Okay. What happens? What happens to? Okay. What does your body eventually have to do, though?
Has to go back.
It has to go back down, right? So if I'm up at the top of this Ferris wheel, eventually I got to come back down. Which means what has to be true about green versus blue?
They cancel out.
If they canceled out, what would I just do?
Oh, dang it.
Okay. Green's got to be a little bit bigger, okay? And we see that that's the case here in this problem, okay?
Yeah, but
Normal force comes out less.
You go up, but then you go back to the same spot that you were at.
Okay,
So,
true. But you're changing as you go along, right? You're
Right.
slowing down, you're speeding up, so these forces can't be equal, right? Or else you just go in a straight line.
I feel like that's
So
what
what
you do in
happens if
Ferris
you're
wheel.
somewhere in between, like the top of the bottom?
Well, that gets into components. Let's not worry about that right now. So yeah, let's not go that far, okay?
Never mind.
But, right, the idea that the seat, the normal force provided to you is not as great as it is when you're standing on the ground, right, provides you with the sensation of being less than what you currently weigh. Do you get that sort of floaty feeling when you're kind of going over the top of that hill on the roller coaster, that maybe the seat really isn't quite there underneath you? Okay? Do you know what I'm talking about? Okay.
Like when you loosen it a little, so you just fall out.
Say again. That actually is, I mean, in that case now, JT would add, when you don't wear the seatbelt on the blue streak, okay? Not that I'm advocating that, just if you don't, what?
So you like
Because
slide more.
in that case,
No thanks.
Lori, in that case, if you wear the seatbelt, Now there's another force in this picture. It's the seatbelt. And the seatbelt pulls this way as well. So you don't get as big of a difference between these two, which doesn't give you as much of that sensation of, whoa, which that you wear the seatbelt, right? JT on the other hand, right? Yeah, JT?
Yeah, when you fall out.
No, you won't fall out, but you get a little bit of like a sensation that you're not going.
On the
Now,
Millennium you would though, wouldn't you?
maybe not fall out.
You
Because
really wouldn't?
no, because they can't engineer it that way. Like the government would have a problem with that. Okay?
I feel like there's a-
But hold on.
I'm not gonna wear my seatbelt.
Let me finish this real quick. Hold on.
Okay.
So, the point being though, that could we engineer it somehow that when you're going through this point, gravity would be the only force acting on you, providing you with the centripetal force that you need at that point. Which way does gravity point? Towards the middle. So could it be solely responsible for the gravitational force or for the centripetal force that you need to make it through this point?
No.
The answer is yes, it could. Okay? At that point, what would normal force become? If we're totally providing on gravity and gravity only, the normal force would become zero. And you would be weightless. Not because there's no gravity acting on you, but because there would be no normal force acting on you. Okay? Could it happen? Yeah, it can happen. Does the government let it happen? No, it's kind of not safe, really. Okay? But it gives you, but it provides you with that sensation of not safe. You know, but anyway, the decreased normal force gives you that sort of floaty sensation. The increased normal force gives you that sort of like weighted down sensation. And that's why we refer to it as apparent weight. Okay. Good.
For the top situation, would it mean that like gravity is the centrifugal force,